तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, today we shall just wind up our discussion on this models of diodes and bipolar transistors. That is, we have seen some models of diodes and bipolar transistors, and the model consists of certain parameters, okay, in terms of which the currents are expressed in terms of the terminal voltages. So, we have to see how to extract these parameters, okay. That is, we must know the values of these parameters in order to be able to use these models properly, okay. For example, if you are, the basic idea is that you may use these models to simulate a circuit, okay, to find out how the circuit behaves, and there these models are used, okay. And the parameter values must be known properly in order to get the proper response of the circuit, to understand how the circuit behaves, okay. So, how to extract these parameters? So, what you have to do is basically you have to take a sample device, okay, do some small experiments and extract these parameters, okay. So, we shall just talk about these things because that is important in order to be able to use the models properly, okay. So, first let us take the diode. Okay, in the diode you have the two terminals, the anode and the cathode, and the current is expressed as call it Vd. Okay. Now, so here you have the parameter Is. So, if you know the value of Is, okay, you would know how the diode current varies with the diode applied voltage. Vd is actually the anode to cathode forward voltage. Okay. Now, so how do you do it? So, basically, if to do that, you must normally, if you see, if you plot the current versus voltage on a linear scale, the characteristics is going to be something like this, okay. So, the diode current is initially very small, as this is an exponential relationship. So, this current, as you see, is very small, but as we increase the value of Vd, okay, it becomes appreciable, all right. Now, in order to extract this, the way to do it is you have to, you see that if Vd is much larger than Vt, okay, Vt is only about 26 millivolts, as we said, at room temperature. So, if it is, say, a few hundred millivolts Vd, okay, this term becomes much larger than 1. So, we can neglect this one, all right, and so we have an exponential relationship, okay. So, if we now plot, okay, so if 1 is neglected, okay, you have ln of Id is equal to Okay. Now, if you plot ln of ID, okay, you should get a straight line. Okay. All right. So, as we said that you should do the experiment for sufficiently high values of Vd compared to Vt. All right. And then this line, if you extend it, okay, this should, the value at this point should give you ln of Is. All right. Okay. Now, I must tell you that there are certain in the actual diode model, okay, there is one small correction factor which is introduced here, which is called the eta, okay, which is called the ideality factor. Okay, and this value is in the range of 1:2, because when we developed the model, we did not take into account certain non-idealities actually, like recombination generation in the depletion region, okay, certain leakage currents. So, these give rise to a factor, okay, which is eta here. So, if you have eta here, all right, so this becomes eta, you have an eta here. So, the slope, okay, of this line is equal to 1 by eta Vt, okay, and Vt, you know, it is a constant at depending on the temperature. So, one can easily evaluate eta. All right. So, this is how one can extract the parameters for the diode. Okay. So, once you know the value of Is for the particular diode, okay, you can use it, use the model. Okay. In fact, all the circuit simulation packages will have certain default parameter. That is, if you don't specify the value of Is, it will take some value of Is and do the simulations, but finally what you get may not be what you expect when you do an actual fabrication, because that Is value, the default parameter, may not match with the exact values, okay, actual values. So, you must in order to get the exact values, one must actually do this experiment, find out Is and use that value in the circuit simulation. Okay. So, this is called extraction of parameters. So, if you have a model, there must be a mechanism to extract these parameters, so that you can use them in the circuit simulation. All right. Of course, in addition, you also have in a diode model, we have already discussed, we also have the capacitances. Okay. Just remove this. Between the anode and the cathode, you have, I think I will remove this. So, basically, I will just draw this model once again. You have a current source which is and you have the so this is the diode voltage, sorry. All right, and then you have the two capacitances. One is the diffusion capacitance and one is the junction capacitance. Yes, you have a question.
Check.
Sir, in eta, how do you fix a number, sir? When you say that eta fixes the non-idealities.
Yeah.
How do you fix particular number to that?
No, when you do that, when you find out the slope of this curve, okay. Now, this has a particular slope, okay. Now, from the slope, one can find out the value of eta. So, if say suppose if eta is equal to 1, okay, then the slope will be 1 by Vt. Okay. If the slope, okay, is, say if eta is 2, it is going to be 1 by twice Vt. Okay. So, this is done experimentally. It is very difficult actually to model the exact value of eta from the model, because this is due to some non-idealities, okay, and one has to really know what are the all these the non-idealities in the device properly to get the exact value of eta from a model. Okay. So, it is usually extracted, okay, once by doing the experiment. Okay. So, this value of eta usually lies between 1 and 2. Okay. So, these are the two capacitances in the device, okay, and we have already seen that the diffusion capacitance, okay, it is equal to the transit time, okay, del okay, and once you substitute this value here, okay, you will get almost equal to, we have already seen that. Okay. And so, to know, so this diffusion capacitance is proportional to the diode current, okay, and the proportionality factor is tau d by Vt. So, this is the transit time, it is the diode transit time. So, one has to know this diode transit time in order to know the diffusion capacitance, and this diode transit time is usually extracted by the transient experiment which we have already discussed. Okay. When you have a transient, okay, the time required for the diode to recover, that is once you have the diode in the forward biased region, okay, and when you reverse bias, that the storage delay time is dependent on this diode transit time. So, it can be extracted from that. Okay. You also have the junction capacitance, which is given by one minus Vd so, this is the diode voltage. Okay. CJO is the junction capacitance for 0 bias. When Vd is equal to 0, Cj is equal to CJO. Now, this I have just written it in terms of M. Okay. When we discussed, we had put half. So, that is for a particular case, that is when the PN junction is an abrupt junction, that is the doping changes from P to N abruptly. But you can have graded junctions, okay, when this value changes. For linearly graded, it becomes 1/3. Okay. So, suppose this is half. Okay. So, again we have to extract the values of CJO, okay, and VBI. VBI is actually the built-in potential of the PN junction. So, once we know these values, okay, we will know the value of the junction capacitance versus voltage. That is what we want to know. All right. So, and also M. Okay. Now, for this, suppose M is equal to half, okay, that is for an abrupt case, then if you plot 1 by Cj squared, okay, and this side if you plot the reverse voltage, okay, that is reverse voltage is actually the negative of Vd. Okay. This Vd is always taken as a forward voltage, okay, that is the convention. So, if you reverse bias the diode and you increase the reverse voltage, what happens? This is going to be a straight line, all right, and if you extend this straight line, all right, the point of intersection here, that is equal to CJO, that is the 0 bias junction capacitance, all right. And if you extend this point further so that it meets this axis, what happens? This is going to give you VBI, all right, because when Vd is equal to VBI, okay, Cj is infinitely large. So, 1 by Cj is 0. Okay. So, you can extract both Vbi as well as Cjo from this mechanism. The problem is you actually do not know, if you are just given a diode, whether it is going to behave in a m is going to be half or 1/3. Okay. So, maybe if you do this experiment, you may find that this is not a straight line, then you have a problem in your hands. Okay. It may be 1/3. So, what you would have to do then in that case, you have to try out different things. Okay. If it is 1/3, then you have to take 1 by Cj cubed, okay, which will be a straight line. Okay. And then you have to do this experiment, okay, and you get the values. All right. So, this is how you extract the parameters. So, once you know these parameters, these diode parameters, okay, for example, in this case you have Is, and here you have the transit time, Cjo, Vbi, m. Okay. You have properly defined the different model parameters. Once you have once you know the different model parameters, you can use it properly, okay, and get the proper device. You can simulate the device in a proper fashion. Okay. You can use this now to simulate a bigger circuit. Is it clear? All right. Otherwise, you have to depend on the default parameters in any simulator, okay, which may not be the exact values, okay, which for your device, and so you may not get the proper results for the circuit. Is it clear? So, extraction of parameters is very important, to know how to extract the parameters. Okay. Similarly, we can now look at the transistor model. Okay, we have already seen that the transistor model, the simple Ebers-Moll model of a transistor, consists of 3 current sources. Okay, so this is the collector terminal, this is the base terminal, and this is the emitter terminal. Okay. This current source value is given by Is exponential okay. This current source is given by Is by beta r exponential Vbc by Vt minus 1, and this current source is given by Is by beta f exponential okay. So, you have these 3 current sources, and from that you can, knowing the 2 terminal voltages. So, if you know the 2 terminal voltages Vbe and Vbc, okay, you can evaluate the collector current, which is the difference of this current source and this one, all right, emitter current, sum of these 2, okay, and base current, which is the sum of these 2 current sources. All right. So, again you have to know certain parameters. What are these parameters? Is, beta f and beta r. Okay. So, how do you extract these parameters? Okay. You do a similar experiment as you have done in the case of a diode to extract Is. You see that what you have to do is you make for the transistor, suppose Vbc is equal to 0. Okay. The base collector voltage is made equal to 0, all right, and then you plot IC and IB versus VBE. All right. Now, what is IC going to be equal to? This current source is 0, VBC is 0, okay. So, this is 0. So, there also exponential VB, it becomes IC is equal to IS to exponential VB by VT minus 1, all right. So, now again just like in a diode, okay, if VB is greater than VT, okay, few times 4 or 5 times, even 4 or 5 times greater than VT, then you can neglect the 1, okay. And if you plot on a log scale, so basically you have to plot on a log scale, okay, this is going to be a straight line, okay. IC is going to be a straight line. What about IB? IB is also going to be a straight line, okay. It is IC by beta f exponential VB by VT minus 1. So, you get two straight lines, all right. So, if this is IC, if this is ln IC, this is say ln IB, okay. This, if when you extend, this is going to be ln of IS, all right. And so, this one is going to be ln of IS by beta f, okay. All right. So, you have two straight lines and the ratio of these two currents, all right, is going to be equal to beta f. So, you see when VBC is equal to 0, okay, the base current and the collector current are related, okay, the ratio is beta f, okay. So, the collector current is beta f times the base current. So, that is the forward beta of the transistor, okay. So, this is how you can find out IS and beta f, okay. How do you find out beta R? You have to do an exactly similar experiment, but this time you have to make VBE equal to 0, okay, and plot IE and IB versus VBC, all right, IE and IB, okay, versus VBC, and again you will get two straight lines and the ratio is going to be beta R. So, you can evaluate again IS from that also as well as beta R, okay. So, that is how you can extract these parameters, all right. So, an interesting thing is that you see for yourself here that when VBC is 0, okay, the collector current is related to the base current, okay, is beta f times the base current, okay. Also, if VBC is negative, okay, all right, which then also you can neglect those terms, all right, exponential VBC by VT terms, okay, with respect to exponential VB by VT terms, okay. And so, when VBC is becoming negative, it actually means that VCE is increased, okay. So, it does not really have any effect on the IC by IB ratio, okay. It still remains more or less equal to beta f, okay, all right. On the other hand, if VBC is made positive, okay, which means that what is it, that VCE is reducing, all right, then collector current is going to decrease, okay. At the same time base current goes on increasing, all right, okay, because the current is the sum of these two, all right. So, keeping VBE constant, if you increase VBC, make it positive, all right, you are going to reduce VCE with the result that the beta of the transistor, effective beta, I mean you should not call it the beta of the transistor, the collector current to the base current ratio reduces. So, you can say that the effective forward gain of the transistor has reduced. You have some question?
VBC
Yeah, yeah, yeah. So there is okay. So some small other effects, okay, which are actually not taken into account for that. Okay, that some base width modulation also takes place, which is going to if the VBC changes. Okay, but that is not really taken into account. Okay, in this. All right. So one has to actually make some corrections to this model. Okay, I think what you're talking of is the early effect. Okay, so this is the basic model, okay, which is used to understand many effects. But if you really want to do, I mean, exact analysis, some other corrections taken into account other effects, like the early effect, okay, has to be done. Because what she's referring to is that if you reverse bias the base collector junction, the base collector depletion width is going to change, which changes the effective base width. Okay, so all this beta, beta f is dependent on the actual base width. So that is going to change. So that is not a constant actually, but dependent on VBC also to some extent. So this model is just the basic model, and so we may have to do some corrections for other effects. Okay. Now, in this model, of course, also you have the device also has the capacitances, okay, which is just like a junction PN junction diode. So between each of these junctions, you have the junction capacitance as well as the diffusion capacitance. So you will have, if I draw it here, the two capacitances here and the two capacitances. So this is CJC, I can call it. This is CDC, CJE, this is C. Okay. So you have the two capacitances. Again, these are the junction capacitances, okay, and they have a similar relation as in the case of a PN junction diode, and they can be extracted in a similar fashion by reverse biasing the particular junction, okay, and evaluating the capacitances. For the diffusion capacitances, okay, they are again related to the transit times. Okay, so the device actually in a bipolar junction transistor, you have two transit times which are defined. One is called the forward transit time, and the other is called the reverse transit time. Okay, what is the transit time? The transit time, as we have defined it, is the ratio of the charge stored to the current. Okay, in this case, in the forward transit time, okay, is given by, so in the when we define all the forward parameters are defined for VBC is equal to 0. Okay, so when you define the tau f, okay, which is the forward transit time, it is for VBC is equal to 0. Okay, so you don't have the reverse the charges due to the base collector junction. Okay, so that is given by Q, okay, by the collector current, okay, the stored charge. So the forward transit time is the stored charge by the collector current, okay, whereas the reverse transit time, okay, so this is when VBC is equal to 0. For the reverse transit time, it is going to be the stored charge, okay, versus IE, okay, with VBE is equal to 0. All right, and again the diffusion capacitance, okay, for this case CDE, okay, will be given in terms of the forward transit time tau f times, just as in the case of a diode, del IC del VBE, okay, which is almost equal to, nearly equal to IC by VT. Okay. All right. So this is of course when VBC is equal to 0. All right. And for this case, CDC will be equal to tau f tau r, sorry. So this is the reverse transit time. Okay. So the reverse, so you have the two transit times, you have the two, so you have the two, so each junction is associated with two capacitances. One is the diffusion capacitance, which is due to the stored charge in the bulk regions, and the junction capacitance, which is due to the charge stored in the depletion region. Okay. So this gives the complete model of the transistor. So these again can be extracted. So the tau f and tau r are again can be extracted, okay, from the transient analysis. Okay, we shall take up the BJT transient analysis later on. Okay, and okay, so this gives us the I just wanted to tell you about how the model parameters are extracted. So once when you discuss a model, okay, it is very important to know, because the model is defined in terms of certain parameters, and it is important to know how to extract these parameters so that you can use that model in a proper fashion. Okay, and you are not dependent on the default parameters provided in any simulator, because they may be wide off the mark, because they may be just some representative values and not the exact values for the given circuit, for the given transistor. Okay. All right. So going back to the bipolar transistor as such, okay, we have seen that if we look at the current voltage relationship, okay, the output characteristics of the bipolar transistor, we have seen that if you plot IC versus VCE, okay, now when VBC is equal to 0, for example, okay, we have seen that IC and IB follow a definite relation. Okay, that is IC is beta times IB. All right, and if you go on increasing the reverse bias on the base collector junction, that is effectively increasing VCE, then the relationship doesn't change much. Okay, it remains it's the same. Okay, so for different values of IB, you will get ICs. Okay, they are separated almost by, if you change IB by the given increments, you get ICs like this. Okay, so these are for constant IB. But when you go to lower values of VCE, okay, which means that basically you are tending to make the base collector junction go to forward bias. Okay, what happens to IC? It reduces. So if you, for the same IB, okay, effectively the ratio between IB and IC is going to be reduced. Okay, so you have the characteristics something like this. Okay, so this is the output characteristics of the bipolar transistor. Okay, IC versus VCE, and of course we shall be using this characteristics, okay, quite a number of times to analyze a given circuit. Okay. All right. Okay. So now from this we now move on to an actual circuit. Up to now we have been discussing the device as such. We have been looking at the device. So for the first time we will now draw a circuit, okay, and see how this behaves. Okay, the circuit which we shall take up is the simplest circuit one can think of, okay, but it is very important in the case of, especially for digital circuits. So you have a voltage here, VCC. This is a resistance, the collector resistance. You have a base resistance, okay, and you have an input voltage. Suppose you have an input voltage here, okay, and let this be the output voltage. all right. So, this is the given circuit, all right. Now, when V in, okay, now in order to understand this circuit or to find out, so this, okay, let us come to this output characteristics. So, this gives us the collector current for different values of base current, okay, versus VCE, all right. Now, if you are increasing the base current, the collector current increases. So, for a given base current, this is how the collector current can vary depending on VCE, all right. Now, if you want to find out the exact operating point of the device for a given base current. So, suppose you are given a base current, what is the exact point at which it operates, okay. It can be operating in any point here, okay, all right. So, you have to draw another line which is known as the load line, okay, which actually is the equation for the load line is, so this is VCE plus ICRC is equal to VCC, okay. This equation must also be obeyed, okay, all right. This is VCE plus ICRC is equal to VCC. So, this equation must also be obeyed, okay. So, now let us draw this line here on this output characteristics. So, this is obviously a equation of a straight line. So, okay, let it be like this. So, this point when IC is equal to 0, VC is equal to VCC, okay, and this point is when VCE is equal to 0, from that equation VC is equal to, okay, yeah, IC is equal to VCC by RC, correct. Okay, so this, so both these equations must be obeyed, all right. Now, okay. So, now suppose IB is very small, okay, it is almost 0, okay. What is the output voltage equal to? So, IB is very small means you have a characteristic curve like this, say at this point, and this is the point of intersection. So, it is operating here, okay. So, VCE, okay, is going to be this, and actually the VCE is itself the V output, okay. So, the output voltage is going to be almost equal to VCC, okay. Now, if you go on increasing the base current, the point of intersection, if IB changes to IB1, okay, the point of intersection is here. So, VCE is going to be equal to this value here, and the remaining part, okay, you see that sum of these two is equal to VCC. So, the remaining part is the drop across the collector resistance. So, if IB is increased to IB2, so this is VCE, all right, and the remaining part is the drop across the collector resistance. Basically, the collector current is increasing, so ICRC is increasing, okay. You go on increasing to IB3, all right. So, this is the operating point, okay. So, what is happening is VCE is reducing, okay, that is important, and the more and more voltage is dropped across the collector resistance, okay. Now, then you increase it to IB4, okay. This is equal to VCE, okay, the output voltage, the remaining part is dropped across VCC, okay. Now, you increase the base current to IB5, what happens? Current does not, the point of intersection remains almost the same, okay. So, the collector current saturates, okay. Initially, as you were increasing IB, IC was increasing, but once you reach this point here, you know, the collector current no longer increases with increase in voltage, increasing in base current, sorry. So, you can say that the collector current saturates, okay. So, that is why in a bipolar transistor, it is this portion of the characteristics which is called the saturation region, Okay, it is in terms of a circuit. Okay, it's not all right. That is, once you reach this portion of the characteristics, with increase in base current, collector current is going to saturate. Okay, it is not going to increase any further. So that is why this portion of the characteristics is called the saturation region. So once you reach here, okay, that's it. The collector current becomes fixed. The collector emitter voltage across the transistor also becomes fixed. Okay, all right. So yeah, and this is the saturation region, and in this region where the collector current increases with increase in base current is called the active region of operation. Okay, and where the base current is almost 0 is called the cutoff portion. So you have the 3 regions of operation. Okay, the cutoff region where the collector current is almost 0. Okay, then you have the active region where the collector current increases with increase in base current. Okay, and then you have the saturation region where the collector current is fixed. Okay, it does not increase with increase in base current. All right. So in a digital circuit, okay, we actually operate the device either in the cutoff or in the saturation region. Okay, so it is either here or there, whereas in a analog circuit usually the transistor is biased in the active region. So that is the difference. Okay, so in this active region the transistor behaves as an amplifier. Okay, whereas here, okay, it is not amplifying, okay, but it is fixed at 2 extremes of operation. Okay, now if you come back to this circuit, all right, now suppose we will just make some assumptions before we go ahead and analyze this circuit. Suppose we say that, you know, it is an exponential relation with the base current and the base emitter voltage. So let us say that when for cutoff, okay, VBE is say less than 0.6 volts. Okay, all right. In the active region, so you are increasing the base current. Okay, so the base emitter voltage, okay, should increase. So let us say it lies between 0.6 and 0.7 volts, and say in the saturation region, let us say VB when it reaches saturation is equal to 0.7 volts. Okay, let us say just this is an assumption. Okay, all right. So just for the sake of doing some analysis. So when V in is less than 0.6 volts or just up to 0.6 volts, okay, what is the base current? Base current is 0. So what is the collector current? 0. So the output voltage is equal to VCC. So let me draw the input output characteristics here. Okay, so output voltage is equal to VCC when V in is 0. Okay, now when you increase V in up to say 0.6 volts, okay, it is the same. It is going to be output voltage is going to be equal to VCC. Now once you exceed 0.6 volts, what happens? This base current keeps on increasing. So as the base current keeps on increasing, collector current keeps on increasing, VC is falling. Okay, so the output voltage keeps reducing. So this characteristic is going to go down like this. Up to what value? Up to here. Okay, all right. So this value is called VCE sat. Okay, that is the VC at saturation. All right. So it is going to go down up to this value. Okay. So this VC sat, okay, normal cases is around 0.2 volts. Okay, so we can write it straight away around 0.2 volts, say. Okay, so this goes down to 0.2 volts, and after that, what happens? if you go on increasing the input voltage, output voltage does not change. All right. So, this is the characteristics of an inverter, correct. So, inverter, because when input voltage is low, output voltage is high. When input voltage is high, output voltage is low. So, this is the characteristics of an inverter, all right, and this is the basic circuit element, okay, in any digital bipolar digital circuit, okay, all right. So, this transistor as an inverter, okay. Now, so you see that using this circuit, okay, we have got an inverter characteristics, okay, all right. Now, this circuit here, all right, is also in this circuit the transistor is also behaving as a switch, okay. It is also called, okay, in this the transistor as a switch, okay. The reason is, what happens when you have a switch? You have, say, a power supply, a resistance and a switch, okay. When the switch is on, okay, or the switch is closed, okay, then the current flowing through the switch is equal to VCC by RC, okay, all right, and the voltage drop across the switch is almost 0, okay. Here also you see, when the transistor goes to saturation, okay, the drop here is around 0.2 volts, which is very much smaller compared to VCC, and you can neglect it, okay. So, it is as if it is a closed switch, the drop across this is 0, the current flowing through it is going to be almost equal to VCC by RC. But when the switch is open, what happens? You have a power supply, all the voltage will be dropped across the switch and current is almost is equal to 0. So, that happens when the transistor is in the cutoff region, okay. When the transistor is cut off, this switch is open, all right, and so what is happening is, so the switch is open, current is 0, and the entire voltage, the power supply voltage, is dropped across the switch. So, basically you see that this is behaving as a switch, okay. So, either when it is in the saturation region, it behaves as an on switch, and when it is in the cutoff region, it behaves as a off switch. So, basically you see, in initial days, okay, the digital circuit began with switches only, okay. You had electromechanical switches like relays, okay, which were used to do digital functions. So, now the advantage is you have a bipolar transistor which is doing the same thing. Now, what is the difference between a bipolar transistor and, say, for example, an electromagnetic switch? Yes, the advantage is an electromagnetic switch you could switch on and off, okay, just maybe a few times in a second, okay, all right. Whereas here you can switch it on and off in millions of times per second, okay. With the applied voltages changing, okay, the switch can be turned on and off, okay, millions of times a second. So, that is the advantage, okay, one derives from bipolar transistor, okay. So, what we shall do later in the course is, we shall see how, I mean, basically you have the different logic families, okay. This is you will find that this circuit is coming on over and over again. You have different peripheral circuits, okay, which gives rise to the different logic families, but this is almost an important component of almost all bipolar logic families, the transistor as a switch, okay. So, we shall, next class we shall actually see the switching performance of these transistors. Okay. Thank you.